A very good noon to all the attendees, and thank you all for joining this eminent foreign lecture series today. So along with me on screen, you can see Professor Dr. Vinuesa KTH, Vice Chancellor for University of Engineering Management, Jaipur, and Dr. Ricardo Vinuesa, who is guest and the keynote speaker for today. So thanks to our VC sir for giving me this opportunity to host this event again. And I welcome you, Professor Ricardo, on behalf of the entire IEM UEM group, and wish that today's session will be a good learning for all the attendees. So before we start the session, I'll just take a minute to introduce Dr. Ricardo. Dr. Ricardo Vinuesa is an associate professor at Department of Engineering Mechanics at KTH Royal Institute of Technology, Stockholm, Sweden. And he is also a researcher at AI Sustainability Center in Stockholm and vice director of KTH Digitalization Platform. He received his PhD in Mechanical and Aerospace Engineering from Illinois Institute of Technology, Chicago. His research combines numerical simulations and data-driven methods to understand and model complex wall-bounded turbulent flows, such as boundary layers developing around wings, obstacles, or flow through ducted geometries. So Dr. Vinuesa research is funded by Swedish Research Council and the Swedish E-Science Research Center. He's also received the Goran Gustafsson Award for Young Achievers. So you must visit his research group web, vinuesalab.com, where you can find the applications of AI to tackle problems of fluid mechanics engineering. And about the topic, I'd like to brief that the advent of new powerful deep neural networks, DNNs, have fostered their application in a wide range of research areas, including more recently in fluid mechanics. So in this presentation, we'll cover some of the fundamentals of deep learning applied to computational fluid dynamics, that is CFD, and furthermore, we'll explore the capabilities of DNNs to perform various predictions in turbulent flows. We'll also cover the convolutional neural network CNNs for non-intrusive sensing to predict the flow of turbulent flow channel based on quantities measured at the wall. So that was a brief about Dr. Ricardo and the topic for today. From here, I'll hand it over to you, Professor Ricardo, and you may please address the attendees. Thank you.
Thank you for the introduction. Can you hear me well?
Yes, sir. We can hear you and you're audible.
Very good. And you can see, hopefully, my slides in full screen, right?
Yes, sir.
Okay. Let me just go back a bit. Yeah, so thank you for the introduction and the kind invitation to this nice lecture series. As mentioned in the introduction, I will talk about artificial intelligence, computational fluid dynamics, and sustainability, and how they are connected. My research is funded by the Swedish Science Research Center and the Goran Gustafsson Foundation. So I'm going to answer two questions. First of all, how to use AI for sustainability. And the second one is how to use, in a more engineering application, how to use convolutional neural networks for spatial predictions in non-intrusive sensing in complicated fluid mechanics problems. So let me start with the sustainability part. Essentially, what we want to do is answer the question of whether AI can be an enabler or an inhibitor for the Sustainable Development Goals. These goals adopted by the UN, the United Nations, to have a sustainable agenda by 2030. And to do that, because these goals are very broad and span a wide range of areas, we assembled a multidisciplinary team which included all the different areas of knowledge that we needed in order to tackle this complicated question. You can see the work in this article in Nature Communications. You can download the reference, and there will be a very detailed description there. Here I will just highlight some of the most important examples. This is the team that we have. So this is AI and sustainability. We have experts in applied AI, theoretical AI, social interaction, ethics, biodiversity, and energy and sustainability. And also we have Max Tegmark, who's a well-known expert in applied AI with kind of like a future vision of how this technology will develop and how it will affect us in the mid and long term. So the first thing that we did was to take the 17 Sustainable Development Goals that you can see here, and these are the 17 goals of the UN, and we divided them into 3 main areas. So the areas were society, so the goals related to society, the goals related to the economy, and the goals related to the environment, so that we can analyze things in a bit of a more, well, in a broader way, essentially. And if you're not familiar with these goals, there are 17 big targets, but within those 17 there are sub-targets. This is what is called here targets, and there are 169 in total. So these go from, as you can see here, from quality education, no poverty, sustainable life below water, climate action. So essentially, we have a total of 169 targets. And what we did was to evaluate whether AI, artificial intelligence, can be an enabler or an inhibitor for each of those targets. And 79% of those targets can be positively affected by AI. That's what we find, whereas 35% of those targets can have a negative effect from the development of AI. Now, it's important to highlight that even if there seems to be a positive effect of AI, the negative consequences should not be underestimated, because even one target with a negative effect could be completely overwhelming all the positive effects that we can see on the other side. So it's important to be aware of that. The environment has a quite positive effect, with 93% of the targets being positively affected by AI, whereas the economy is perhaps the area with the lowest benefit, only 70%, and I'll be talking about that in a minute. Now, this is kind of like a general overview of how AI can help us in a wide range of areas. Later in the presentation, I will go into examples of engineering, of fluid mechanics in particular. That's my main area of expertise. But if you look at the detail of all the SDGs, of all these goals of the UN, there are many, many different categories, and are quite wide range of applications where this can be helpful. On the left, you can see this wheel with all the goals, and I'm reporting the positive effects of AI. And on the right, I'm reporting the negative effects of AI. You can see 2 lines, a thinner one and a thicker one. The thin one is the line corresponding to whether there is a documented relationship between AI and that particular SDG, that particular goal. And the thicker one, I will get to it in a second. As you can see intuitively from this spider charts, the 79% that you can see here clearly shows that AI has a quite some positive potential on a wide range of areas, whereas the negative effects are quite more limited and restricted to just concrete applications. Now, what do we do? Well, in the first part of the analysis, we just were interested in finding whether there was an influence of AI. But in the second part, we wanted to look at the types of evidence. So we wanted to see basically what's the quality of the evidence that we can find. And to do that, we divided all our references into 4 categories, going from A, B, C, and D. So an A reference is a reference where what we have is quite a very strong evidence of the connection between AI and that SDG and reproducible results. And then we go down in this category of strength of the evidence, with the lowest one being the D category, where the references are basically speculative or not so easy to generalize. And what we do is that we introduce a weighting factor. So in the case of very speculative references, then we have a 0.25, meaning that only 25% of that target is positively or negatively affected by AI. And now, looking again at this figure, what we can see is that, of course, the thick line is smaller or equal than the light one, because the weighting factors go from 0.25 to 1. And when we take into account the strength of the evidence, what is interesting is that the evidence documented positive effects on the environment and the society are quite strong. So if we take into account all these SDGs, what we see is that we don't reduce so much the positive effects of AI when taking into account the strength of the evidence, the negative effects are a bit more speculative. However, the economy is different. As you can see in this sector over here, the thick line is quite reduced compared to the thin one, meaning that the positive effect on the economy are not sufficiently documented, and that's these effects are based on more speculative studies. So that's something to keep in mind when it comes to future development, because of course now everybody is talking with the fourth industrial revolution of the effect of AI and how it's going to affect our businesses and our economy and our lives in general. It's quite important to keep in mind that the positive effects are not so well documented. Some key results, some examples, and again, you can go to this article in Nature Communications to see a very detailed account of all of this. But in general, AI is enabling new technologies that were not available before. So, for example, in the context of SDG 1 and no poverty, it's possible to use satellite data to track poverty, to track areas of poverty, and hopefully develop measures to help those areas. A negative effect. Well, if the future is going to rely on AI heavily and we have uneven opportunities to access AI, then we're going to increase the already existing inequalities, and therefore we will be in a worse situation than we started. So I think it's quite important to be aware of this potential, but also of these possible risks associated to the technology. Of course, now we live in complex times in the context of the corona pandemic, and we live in a quite polarized society. And social media and AI algorithms that are used in this technology, well, this is not helping with this polarization. So these algorithms are not only creating a more polarized society, but also they are producing effects in outcome of elections, outcome of public debate, and social image of the decisions being made in the government. So it's quite important to be aware of this potential for polarization. What I would argue in the context of SDG 16 for strong institutions is that there should be regulatory oversight for AI. I mean, there should be regulations, but this should be preceded by insight, meaning that what we need is experts in the groups that are developing the policy and are developing the regulations for AI, and to try to make scientifically based decisions rather than politically driven, as unfortunately we can see nowadays that a lot of politics are influencing the decision-making process, and it should be experts, the ones that are really helping in this process, and also to have the public, the general citizens aware of the possibilities and the risks associated to AI, so they can join a global debate, because this technology is going to affect everybody in a few years, and it's important that everybody is aware of what can be done. Another example of data-driven technology, this is also more related to Corona, is in the context of the digital contact tracing. So these apps that were discussed extensively a year ago, and well, they would have helped a lot to handle the pandemic, but in the end, they were not so extensively deployed. This has, of course, important applications on SDGs 3, on health, and 10, on inequalities. And we developed an ethical framework. You can see all the information here in Results in Engineering. This is not a journal, and you can see the article here. What we did was to basically develop a series of guidelines that these apps should fulfill in order to respect the rights of the citizens and the freedom. So we don't compromise the situation of the citizens. And one of the main conclusions is that we should have a decentralized data gathering. A good way to do it is the DP3T protocol. So we should not gather data centrally. It should be gathered in the individual phones so that nobody can really access and compromise the data of the individuals being collected. So this is about data-driven methods and sustainability, and perhaps a summary can be given by this figure that you can see. And of course, what we see in the interactions between technology, individuals, and government is that the technology is advancing extremely fast, much faster than individuals can react to it, and that's also much faster than the governments in the legislation who are lagging behind. So governments need to catch up with the technological developments, and to do that, they need to incorporate experts who know about the technology that is being regulated. And the environment acts as an underlying layer where we have positive and negative effects, but also resources. And hopefully we are also having an impact on the environment that is not critical. That's related, of course, to the current climate crisis, which is a whole different topic. So these agents are interacting in this way that I'm showing here. And related to the environment and trying to exploit all the potential of AI and all the possibilities of basically getting the best out of the SDGs, I would like to bring up the example of SDG 11 on sustainable cities, which is, of course, a very important problem because 800,000 people die in Europe every year due to pollution in urban areas. So clearly this is somewhere where we need to act, and we have seen in our article that AI has a huge potential to help here. And now I will transition a bit towards the more engineering part of the talk. I wanted to kind of bring some context into how AI is helping us in many areas, how AI can be detrimental in other areas. So we have to be aware of the pitfalls. And I'm going to go now into detail into this application. So how to use AI for non-intrusive sensing in urban areas. So what is non-intrusive sensing? What this means is to measure something without disturbing it. So if you have, this is an example of a building that you can simulate with a lot of detail with supercomputers. And if you try to measure the flow here and the wind in that street, then you're going to disturb it because the probe that you're using is affecting the velocity that you're actually trying to measure. But what we can do is to use non-intrusive sensing. So these black dots that you see here, these are sensors that are located on the surfaces of the city. And what we do is that we try to combine simulations and AI, deep learning, to reproduce, based on these sparse measurements, three-dimensional fields of the velocity, of the temperature, and the concentration of pollutants in that urban area that we're considering. So this, in principle, has a lot of potential to obtain more sustainable cities and to lead to solutions that are beneficial for everybody. And here is a little summary of current work in my group. You can see on the right different simulations. These, by the way, are very, very detailed simulations using high order spectral methods for the ones that are more familiar with fluid mechanics. And this is computational fluid dynamics, CFD. And here I'm simulating two buildings with different separation between those buildings to try to model the different regimes that are present in a city. You can see all these results in this article that we have recently in Energies, so you can see some of these results. And here I summarize some of the reconstruction methods, so some of the ideas that I have to go from the sparse measurements to the densely resolved flow fields. Okay. I will not go in a lot of detail on this. I'm going to show a simpler example that hopefully will help us to illustrate the type of application that I'm talking about. So basically, predictions of spatial distributions, non-intrusive sensing, which means to take few points, okay, in our domain, in this case, in the walls of the city or in the ground, and from those few points to be able to reproduce the three-dimensional velocity field, concentration field, and temperature field, okay? So to do that, we're going to use a simpler geometry. We're not going to consider the whole city. We're just going to consider a channel. I will tell you more about it. And there has been quite some literature in the fluid mechanics community on how to do this, and this non-intrusive sensing. Traditionally, this has been done with linear methods, and basically establishing a linear relationship between the input, which is the information at the wall, and the output, which is the flow above it, using linear stochastic estimation, extended POD, and these are methods that are linear. You can see I actually have also an article, Sasaki and others in the Journal of Fluid Mechanics, where we compare, here is the near wall fluctuations the reference, and here are the predictions with a linear method. Now, what happens with linear methods? Well, turbulence, for the ones who are more familiar with fluid mechanics, turbulence is non-linear, which means that there are very strong mechanisms of modulation, which cannot be reproduced by a linear method. I mean, it's a very complicated phenomenon, and using a linear method is not accurate enough to do the prediction accurately. That's why we argue that neural networks, which have the possibility of doing those nonlinear predictions, may be adequate to capture the nonlinearities and improve the prediction capabilities of these techniques. And as I was mentioning, we consider a simple case, a simple channel. In this case, we have on the bottom, we have a wall, and on the top, we have a free surface, a symmetry condition. So this could be a model for a river, for example. And we use the Fourier-Chebyshev code Simpson. This is a very widely used code at KTH with a very standard discretization. And we're going to do what is called DNNs, and direct numerical simulation. So we're going to do a very detailed simulation of this flow to produce training data for our deep learning models. So we have a friction Reynolds number of 180. This is a low Reynolds number, but turbulent, so enough to get some results and some proof of concept. Sorry for all the slides. And then you can see a very detailed description of all of this in this article by Guastoni and others, a PhD student in my group, in the Journal of Physics conference series. There are two types of neural, well, there are many types, but we're going to focus on two easy examples of neural networks. First of all, we have networks that are fully connected, which means that each neuron of one layer is connected to all the neurons of the next one. And these ones are very widely used. They're very easy to use, but they have one problem, and is that if you require a very large number of parameters, because all these connections have weights and biases associated to them. So essentially, if you have fully connected networks, you need a lot of parameters to train them, and then you are prone to overfitting. However, there's another type of network, like the one that you see here, which is called convolutional neural network. In these networks, what you have is that you have an input, which is this field here. You have this little window, and that's a kernel, and this window can be just by 3 times 3 or 5 times 5 points. And this window, what it does is that it's sweeping the input domain, the input field, and conducting a convolution operation. So a convolution operation, what it's telling me is that one output point, this is the feature map, this is the output. So this output receives information from all these 9 inputs here. And so this little window is going through the domain. And what that means is that I don't need so many parameters, because not all the grid points in the domain are connected. I only have the parameters associated to the window. And this is extensively used in computer vision, because it's easy to train, or relatively easy to train, and also we don't require so many parameters to identify local features. So what we will do, going back to my channel example, is to use the information at the wall. This is this blue surface here. Remember the example of the building that I showed before. I'm taking sensors at the wall, and I want to predict the flow above the wall. So I'm going to predict the flow on this yellow plane that you can see here. So I'm going to use as an input the two wall shear stress components, and the wall shear stress in the stringwise direction and in the spanwise direction at the current instant. I'm going to use a convolutional neural network to make a prediction of the stringwise velocity fluctuations at this location, so above the wall. I take the wall information, the sensors, and then I predict the flow above the wall. Okay. And again, this is all documented in this Journal of Physics Conference Series article that you can find here. So what do we do? Well, we consider this architecture that you can see here. This is a convolutional neural network, fully convolutional, and we have 2 inputs here, the 2 wall shear stress components. We have 1 output, that's the stringwise velocity fluctuations, and we have all these hidden layers in between. We have a total of 5 hidden layers, well, actually, we will have a documentation of all the feature maps that we are getting. So in total, we're going to do 6 different convolutions. And this works like this. In the first layer, this is the input. In the first layer, what we do is that we take this kernel and we conduct convolutional operations to extract features from that input. We use the rectified linear unit activation. We have a total of 6 layers, but 5 series of feature maps. And the depth, this number here, is the number of stacked layers. Let me explain that a bit better. In the first layer, in the first hidden layer, what we have is a filter with a depth of 2, because I have 2 inputs, and a kernel size of 5 times 5. So I only have 50 parameters. The little window that I mentioned before has 5 times 5 times 2 parameters. And in the end, I can sweep this input window with this filter that you see here. If instead of using a convolutional network, I used a fully connected network, I would have a total of almost 33,000 parameters compared to the 50 parameters that we use with a convolutional network. So it seems quite clear that DNNs are more efficient for computer vision because images tend to be quite large, and then a connected network is going to be completely unfeasible. It's not going to be practical at all. However, with this window that is sweeping through the domain, I can have a much more efficient way of assessing the data and exploiting the data for training and for prediction purposes. What do I do? Well, what I do now is that I have a total of 64 filters, which means that 64 features. So what we do is that we apply this filter a total of 64 times, and we have 64 stack layers in this first hidden layer. Each filter identifies a different feature. This is very important. Features, as you saw before, I mean, fluid mechanics is an area where there is a lot of spatial information in the data, and we can use these images where we have quite some spatial information. We can exploit the spatial information, and we can use that to get all these features that we can see here. Features can be a low-speed region, a backflow region, a constant region of high fluctuations. All of those can be considered features in this context. In the next layer, what we do is that we have now 64 fields, so our filter will be of size 64 times 3 times 3. We reduce the size of the kernel because we have increased the depth. And something to kind of keep in mind is that deeper layers, so as we go closer to the output, they identify larger features. Because as we saw before, each output after a convolution gets information from 9 or 25 inputs. And as I do more and more convolutions, my outputs are getting information from more and more data points. So essentially, we are getting more and more information, and these layers are capturing, or they are identifying larger features. There are 2 types of convolutions. One is the typical convolutional neural network, which is basically getting an image as an input, okay, like this. And at the end, I have a connected layer to have a global output. This is important because it's a different type of problem. In this case, I take this image, and my output, which is global, is a classification task. I'm just saying that this is a car, essentially. So I add at the end a connected layer to have a global output. If I have a fully convolutional neural network, that means that I don't have any connected layers at the end. They're all convolutions all the way. I start with an image, and then the output is local, it's not global. So at the end, I keep doing convolutions. And in this case, I have a classification problem of this type. So I'm not only identifying that there is a car, I identify that this is the road, this is the pedestrian cross, these are buildings, and this is extensively used in computer vision, or for example, for autonomous driving, as you can see in this example here. So if I do fully convolutional networks, then I can have local outputs. If I do convolutional networks with fully connected layers at the end, what I will have is global outputs. And so I will get all the information, and then the output will not be an image anymore. It will be a label or a string or something like that. Okay, so let's look at the results applied to our channel. What you can see in this slide is the string-wise velocity fluctuations at y plus 15. For the ones who are not so familiar with fluid mechanics, this is the region above the wall with the strongest fluctuations, and the near wall region, basically. And what we're doing is that we have at the center the reference, and you can see fluid mechanics in turbulence. We have these characteristic streaky structures, these elongated things. You can understand now why convolutional networks are quite good for this problem, because there is a spatial distribution, there is a structure in the flow. And these convolutional networks, what they do is that they exploit the spatial information for a training and to make predictions. On the top, you see a linear method to predict this same field, and on the bottom, a deep neural network, a convolutional neural network. And what you can see is that the predictions from the CNN, from the convolutional neural network, they're much better. And in particular, we characterize very well the modulation, so the small scale components of these structures, whereas this one, it just provides kind of like a filtered version of that same field. If we go far away from the wall or farther away, what we can see is that the neural network still predicts very well. The linear method is becoming progressively worse. And very far from the wall, the neural network struggles because we are quite far away, so we don't have such a correlated data set. But still, we reproduce the information, we still reproduce the spatial distributions of the data, whereas the linear method is just providing very wrong information. We cannot provide so much from the linear method. So this is important because we can outperform traditional linear methods by using deep learning, by using methods that exploit the non-linearities in the data. And here is the effect of the time step between samples. Of course, when you're farther away from the wall, the structures are larger and slower. So if I increase the time step, I may be able to get more information, and in this case, I get slightly better predictions when I increase the time step. So that's also something to consider when doing the training, so we can have the most adequate data set in terms of the training and the validation for the case that we are considering. Okay, so this is about the effect of the time step. And here are what we call the turbulence statistics. So the mean of the flow. This is the mean velocity profile, and these are the string-wise velocity fluctuations. And here what we show is in orange the small time step CNN, in blue the large time step CNN, and in green the linear method, linear stochastic estimation. Just to give you an idea, I mean, the near wall peak is very well predicted by the CNN. And of course, the linear method is much worse with over 12% error. As we go farther away from the wall, the CNN is still outperforming the linear method. So neural networks, because they can do, this is probably the most, the take-home message. Neural networks, because they can perform nonlinear predictions, they outperform traditional methods that are based on linear approaches if your system is highly nonlinear, as it is the case of turbulence. Turbulence is highly nonlinear, and therefore it's important to use a nonlinear method to be able to account for those nonlinearities in the data. Okay, I already see some interesting questions, but I guess we will answer them at the end. So more things. This is about the statistics, but we have also more information. This is actually quite interesting, this part of the presentation. I think that it has quite some potential. So we did a low Reynolds number, okay? Reynolds tau 180. Now we increase the Reynolds number to RE tau 550. 550 is already quite a turbulent Reynolds number. We already have a scale separation, so things are a bit more exciting from the turbulence point of view, from the fluid mechanics point of view. It's of course a much more expensive simulation, and what we will do is that we will use now 3 input fields. So we use the 2 wall shear stress components and the pressure at the wall, okay? And we're going to predict the 3 velocity fluctuations away from the wall. So string-wise, wall normal, and span-wise velocity fluctuations. We will use periodic padding as well. And all these results are going to be found in this preprint in archive. So you can find everything here, all the details, or any questions that you have, you can of course ask me. But all the documentation of the method is in this archive article. Okay. We also consider, in addition to the fully convolutional network approach that I mentioned before, where I just take the input and I predict the output field, another method that combines fully convolutional network and POD. What is POD? I mean, for the ones who are not familiar with it, it's a proper orthogonal decomposition, where what I do is that I take my signal, in this case the velocity, which is a function of space and time, and I decompose it into spatial modes and temporal coefficients. So I basically separate the spatial information and the temporal information. And what I will do is that I will predict the temporal coefficients having the spatial modes fixed. This is quite important because in a way the POD modes and these spatial modes, they're encapsulating part of the information, and then I don't need to worry about predicting the spatial part. I only need to worry about predicting the temporal part. And this will have an impact in the predictions, as we will see in a minute. Okay. So this is the FCM POD. These are the instantaneous predictions at tau 550. You can see that this Reynolds number is higher, and therefore the structures look, I mean, the spacing in the near world region is the same in plus units, but of course in outer units you see smaller structures. The third row is the DNS, that's the reference. Okay. The first row is extended POD, which is the linear method, equivalent to the linear stochastic estimation that we showed before. So this is basically the linear method. Second one is the FCN POD, and the last one is the FCN. So the FCN is what we showed before. FCN POD is the new method that encapsulates the information, spatial information in the POD modes. I will show quantitative data in a second, but for now we can see that the extended POD, the linear method, I mean, is worse. This is a region close to the wall. This is a region far away from the wall. The FCN method is very good close to the wall, and far from the wall, the FCN POD is better. And we will talk about that a bit more. But essentially, doing the whole prediction is good close to the wall. Doing the prediction based on POD modes is better far away from the wall. And these are the statistics. Here, I mean, I would say that it's very remarkable that I can predict the stringwise velocity fluctuations with less than 1% error, the near wall peak. The wall normal and span-wise fluctuations, they're also reasonably good. Of course, all the predictions get worse farther away from the wall, because the wall information, which is my input, is not as highly correlated with the information far away from the wall, but still I can get quite good predictions, quite reasonable predictions. And something quite important as well is that you can see how far away from the wall the blue dot, which is the FCM POD, slightly outperforms the orange triangle. So close to the wall, the fully convolutional network performs better. Far away from the wall, the FCM POD performs better because the larger scales can be more easily encapsulated into few POD modes, for which we only need to predict the temporal dynamics, whereas close to the wall there is a wider range of scales that complicate this way of encapsulating the information in few modes. You can see that even far away from the wall we get a 25% error, which is actually quite remarkable, and the extended POD is always above 45% error. So that's also something quite important to keep in mind. This is the stringwise velocity fluctuation results. Now, this is, I think, my favorite part, and I would say the most important for many applications, not only for fluid mechanics, but for many applications. This is transfer learning. What is transfer learning? Transfer learning is the possibility of using the information that we learned for one network, for one model, in another one. Okay, so this really has a huge potential for many areas, and in this case we're going to illustrate two examples to improve the training. The first example is shown here in this paper, Journal of Physics Conference Series, and what we will do at Reynolds tau 180 is to take the model that we used to train at y+15, close to the wall, and use it to predict at y plus 50, far away from the wall. Now, remember that I mentioned that the layers that are closer to the output can predict larger structures, and farther away from the wall, we will have larger structures. What we're going to do is that we're going to freeze the first layers, which are going to, the three first layers, which are going to predict the smaller features, which are more similar. And then the larger features, which will change as you go farther away from the wall, will be retrained. So we only train 3 layers, and the other 3 are fixed from the previous example that I showed. And what you can see is that we can get essentially the same error, and this second line is the errors in the transfer line. So the same level of error at 1/4 of the computational cost. So I only need to train 1/4 of the time, because I only train these 3 layers, and I obtain the same accuracy, which is quite cool. And even more exciting is, can I predict at 550 using the network at 180? And what I'm showing here is basically taking the network that I train at 180 and initialize the training for 550 using those weights. So I train the network at 180, I take those weights, and I initialize the train at 550 with the same weights that I had at 180. So I transfer the initial condition, let's say, of the weights for 550. And what you can see here in this figure, by doing different tests, is that with 25% of the data, I can achieve the same level of accuracy that I have with 100% of the data and random weights. So what does this mean? Well, this is quite exciting, because a simulation at 180 is orders of magnitude cheaper than a simulation at 550. What this means is that I can train a model at 180, which is very cheap. I can create as much training data as I want. I train it, and then I use those weights to initialize the train at 550 and reduce the requirement of data to 1/4 when I do the 550. Of course, this presents us with a huge opportunity for improvement and a huge opportunity to save computational cost and training cost by exploiting what has been learned in one case to another one. So we should really always focus and benefit from these possibilities of doing transfer learning. And this is one last application. I also enjoy it very much. This is super resolution, right? So I mentioned that we are measuring at the wall, and we want to predict the flow above the wall. But and you remember at the beginning that I just had few points, a few sensors. But everything that I have shown you so far assumed that I had a densely resolved wall information, that I knew everything at the wall, so I could predict the flow above the wall. In reality, that's not the case. In reality, I don't have all the information at the wall. I will have just few points, few data points, which are the sensor locations. And therefore, what we need to do in order to improve the predictions is to first take the information at the wall, which is coarse, which is only a few grid points, and increase the resolution of that wall information before doing the predictions of the flow above the wall, essentially. So this is something that we have done recently. You can see the details here in UEMs and others, and this is the archive preprint, and it has just been accepted in Physics of Fluids, so you will get the article available soon as well. And we're going to use a type of network called GANs, Generative Adversarial Networks. How does this work? The GANs basically has two parts, a generator and a discriminator. The generator, what it's doing is learning how to create good high-resolution images from low-resolution ones, so increasing the resolution using labeled training data. And the discriminator is trained to identify whether this is a real image or a fake image. So if this belongs to the original data set or it was just created by the generator. And there is a little bit of game theory here in this training process, because these two networks fight against each other to get better. And the generator gets better at creating fake images, and the discriminator gets better at identifying those fake images. That's a very efficient way of training this architecture. And what we get, what you can see here on the upper right part, is our schematic. So we have the three inputs, the wall shear stresses and the pressure in low resolution. In the first step, we create high-resolution versions of these inputs. And in the second step, we use those high-resolution inputs to predict the velocity fluctuations above the wall. So you can see how we go from sparse measurements to dense predictions of the flow. And here I'm going to show some sample results of the wall reconstruction. This would be the string-wise velocity fluctuations. This is the DNS, this is the reference. On the first line, you can see the input with progressively larger downsampling. This is a factor of 4, of 8, and of 16 in each direction, which means that this input is 16 squared times coarser than the input, than the reference data. And on the bottom, you see the predictions. Now, I would say GANs is very good at creating images that look realistic. And this is something that we have seen, I mean, all the face apps, for example, on your phone, all these deep fake videos that you can see in YouTube, all of that is created with variations of this architecture. So this architecture is very good at creating images that look realistic. They don't have to be perfect, but they fulfill or they contain the statistical properties of the reference. And what you can see is that all the predictions look very realistic, even if they're not exactly the reference. I would say that in cases of downsampling 4 and 8, we are in excellent agreement with the reference. But even in this case, where I just have few sensors, I get some attenuation of the fluctuations, but you can see that the structures and their size, their location, their spacing, they are in very good agreement with the reference. So we are actually able to obtain very realistic flow fields using an input that, as you can see, is extremely coarse. I mean, from this, the fact that from this, which basically tells me nothing, I can reproduce this, it's really amazing. I think that that's very, very encouraging. So this means that GANs for super resolution can also be used in the context of fluid mechanics, and in particular with the idea of non-intrusive sensing from few sparse measurements. Okay. And this is a bit of a wish list, no? A Santa Claus letter. What do I want to do in the future? And well, I mean, we have shown that there is quite some feasibility of using neural networks to predict turbulent flows. We can use it to predict boundary conditions or inflow conditions, to do stability scale modeling, for structure interactions as well. Flow control, which I didn't mention so much, but one big motivation of all the non-intrusive sensing data and results that I presented today have the motivation of flow control, and autoencoders for model reduction, where we are also very, very active. And this will be a summary of my presentation. The first part about AI and SDGs, and remember that a big 79% of the targets can be positively effective, and 35% have a negative effect of AI. We have to be aware of the limitations, and there's a big need of a global debate. And in the second part, I showed that it's possible to obtain excellent predictions of complex turbulent flows with CNNs, with convolutional neural networks, in particular getting less than 1% error in the near wall peak, outperforming linear methods. This is very important. And well, there's some possible improvements. I would like to thank you very much for your attention. This is my web, vinuesalab.com. So if you have ideas or you want to collaborate, feel free to reach out, and we can have a discussion about what are the interest areas that you have. We offer master thesis as well, and research collaborations. And yeah, thank you for your attention, and I will now take your questions.
Thank you so much, Professor. It was really a wonderful lecture. And Professor Umesh Gurnani is over here. I'm sure, Professor, you have some questions in the questions box. I will request you to read those out, please.
Yes, I'll just read out the questions. So, Professor Ricardo, like the first question which I can see is, can machine learning replace CFD, computational fluid dynamics, in future?
Yeah, that's a good question. I don't think that it will replace CFD. I think that it can augment and help with CFD. I'm actually working on different applications in this direction. I mean, the way that I see it is you have a system for which you know the equations, right? That's the Navier-Stokes equations, which govern the flow fields. And that's the most compact representation of the flow, right, of that behavior. Now, to solve that numerically, there are very established methods, numerical methods, that's CFD. However, there may be areas where CFD can help. For example, to speed up certain parts of the iterative process of a CFD solver. There is an area which I didn't mention today, but I'm quite active on it, which is PINs, physics-informed neural networks. And that's being used also to solve certain fluid mechanics problems and certain CFD problems. So there are some interesting directions. I would say that CFD will not be replaced by AI, but it would be augmented, or it will be helped to perform more efficient simulations with AI.
Yeah, Professor Ricardo, I agree with this. So I'll move on to the next question. It's in CNN architecture. You had displayed a slide on CNN architecture. So the question is that, does it matters if number of layers increase or decrease between the input and the output layers?
Yeah, I mean, of course, there are many parameters to tune. And then one can play with the number of layers. One can play with the size of the kernels. One can play with the amount of feature maps that are being stacked. So this was a bit of trial and error. It's not necessarily an optimal architecture, but it provides very good results. And I would say that it's important to have several hidden layers in the context of fluid mechanics. I'm talking about fluid mechanics, not other problems, because the layers closer to the output, they're looking at progressively bigger features, whereas the first layer, they're looking at the smaller structures. And because turbulence is a multi-scale phenomenon, it's in principle beneficial to have that, to have several hidden layers to see that scale disparity and to make predictions that are reasonable. How many layers? That depends on your problem.
Okay. So Professor Ricardo, I'll move on to the third question. That is, can we control the turbulence in fluid flow using AI or ML? Yeah,
there's quite some work, and I'm working on different directions to kind of go beyond traditional methods of control. So yes, there is quite some potential there, but it's still a little bit early, I would say. Because turbulence, I mean, it's easier to control flow around a 2D cylinder, for example. Turbulence is a bit harder to control, but I'm quite optimistic that there are some deep learning approaches to control the flow in a turbulent scenario.
Okay. So we do have a next question, that is, can we control the Reynolds number of a particular liquid using AI or ML?
Yeah, that's I mean, in the end, the Reynolds number, it is connected to the status of the flow that you have at a certain moment, right? I mean, it's connected to, for a given fluid, if we don't change the fluid, it's connected to the size and the speed of the flow. And of course, if you have a given geometry in a given fluid, the only thing that can change is the speed, right? One can control the flow with AI and produce laminarization, for example, go to laminar conditions. One can design some algorithm that is going to attenuate certain structures. One can reduce the speed of the flow to reduce the Reynolds number or increase it with a certain pattern given by an AI algorithm. But I would say, I mean, of course, one can also use AI to optimize the geometry and change the geometry. But maybe the most reasonable way of changing the Reynolds number is changing the speed with a certain control law that is prescribed by an AI algorithm.
Okay, so Professor Ricardo, within the next question, it is similar to the previous one only. Like, can AI help us in calculation of viscosity of a particular fluid?
Yeah, I mean, AI or deep learning, machine learning, depending on which method, but it's very good for regression problems, right? So I mean, of course, there are experimental ways of measuring the viscosity, as you all know. But I would say that, I mean, probably you want to do it in a scenario where it's not so easy, right, to do that, to use the viscosimeters. But then you can probably develop the AI methods to correlate something. Like, let's say that you can measure of a fluid the speed, or you can measure the luminescence, or you can even illuminate it with a certain light and see what is the refraction of that pattern. Then you can develop some deep learning method to connect that measurement, indirect measurement that you have, with the viscosity. So, I mean, it would have to depend a little bit on what you are thinking when you make that question. But in general, I would say that it can be used to correlate an indirect measurement with the viscosity that you want to measure.
Okay, and we do have a last question. That is,
Yeah.
What are the limitations of AI algorithms in fluid mechanics?
Yeah, that's a bit of a quite a general question. I would say that it's very important to know a little bit about, I mean, before applying AI or any new technology to a problem, that you should learn about that technology and choose the right problems. In the context of machine learning or deep learning, to really understand what this technology is good for and find the right problems for this type of technology. For example, the non-intrusive sensing is an interesting problem because then you can exploit the spatial information of the data. But I would say that if there is a physical law governing a certain mechanism, then you shouldn't use AI. You should use that physical law because the physical law is going to be the best representation of that phenomenon. So that would be one limitation of AI. I mean, when there is a physical law. And also, I would say that, of course, with uncorrelated data, if there is no way to get a decent correlation, then it's going to be very difficult to get a good algorithm to make predictions. Even if you have a huge network and a huge GPU, I mean, if the data is not correlated, if you're trying to find a prediction of something from an input that doesn't have any connection with that output, then probably you will not get a good result, regardless of what you do. So I would say those are two of the limitations of AI in the context of fluid mechanics. And maybe I can add also something. I mean, there are sometimes traditional methods to do things, right? And those methods are cheap, usually cheaper. I mean, AI in general is expensive, computational expensive. So you should not use it blindly. You should know the application that you're trying to do, and you should have a good reason to use AI instead of a traditional established method that can be cheaper and with a similar accuracy.
Okay, Professor Ricardo, like we do have one more question in the chat box. That is, I don't know like how it is related to AI and fluid mechanics. Like, can attacks be launched on the eye of cyclones and weaken them?
I didn't hear. Can what be attacked?
Can attacks be launched on the eye of cyclones and weaken them?
But what is the? Yeah, I'm not sure what is the connection exactly. I mean, what do you want to put in the cyclone? Is it like a sensor, or I didn't hear so well? What do you want to do?
Question is from Professor Arun Kumar Chatterjee, and Professor Gurnani, if possible, should I unmute him? If then he can directly ask.
Yes,
I think
yes,
there is
that is better.
It is like some confusion. Just a minute. So Arun sir, I'm just unmuting you because there is some. Okay, I have unmuted you. You may kindly unmute yourself and ask, sir. Yes, please.
Thank you. Thank you very much. Good afternoon, sir.
Hi.
You see, my question stems from the fact that a cyclone is essentially a flow of air, very turbulent, very strong with high speeds. Now, there is a formation period of a cyclone. It resides on top of the sea or ocean. For example, as far as we are concerned here in Kolkata, the Bay of Bengal is where all cyclones form. So I was thinking in terms of, using AI, ML, and all the developments that we have now to get perhaps under the eye of the cyclone and, reverse the direction of its build-up. So if it is building up in a clockwise direction,
Yeah.
we can perhaps weaken it by giving an anti-clockwise, signal. That means, I'm negating the force of the flow in the positive direction. That is my question.
Yeah, no, I
It's
understand.
very difficult to put all this into words. So I raise my hands. Thank you very much.
No, but it's an interesting question. Yes. I mean, first, I would say that I work with experts in climate modeling to use AI they use simulations, large-scale simulations, and we use AI to try to improve the prediction capabilities of these models with super resolution, for example. So what are, in my climate model, what are the things that happen prior to a cyclone, for example, right? So you can maybe use AI to predict better whether a cyclone is going to form or not. That's one thing. The other thing that you mentioned about controlling, in principle, yes. In principle, the problem is that you would need a lot of, I mean, if we assume that we know the velocity distribution of the cyclone, you can have a certain control with some blowing suction, with some rotation at the eye of the cyclone, and then develop a data-driven algorithm to try to control it and attenuate the fluctuations. So in principle, from a theoretical point of view, I think it's doable. It could be an interesting problem, but in practice, of course, one needs to think that you need to put something there, right? The actuator and the sensors to be able to see what the velocity looks like. So probably the practical implementation would be difficult, but I think from a theoretical point of view, it could be done and it could be interesting. I hope that answers your question.
Yes, Professor Arun. Professor Arun Kumar Chatterjee, can you kindly say your answer is okay now? So you have got your answer, I believe. Okay then.
Yes, absolutely. Thank you very much. Because you see, I asked this from the point of view of environmental safety.
Yeah.
In places that is along the coast of India, the eastern coast, and all the way to Bangladesh and all that, we have a lot of cyclonic interference that affects the lives of millions. They go without food, they go without water, medicines and all that. So that was the origin of my question. Thank you very much for the answer.
I actually think that I mean, controlling it can be possible, but challenging. I think that maybe the interesting direction could be to improve climate and weather prediction models with AI, so you can predict better the formation of these cyclones. And then before it happens, then you can evacuate, and then you can use it like that. Because of course, I mean, yeah, there are some indicators of whether it's going to happen or not, but using AI, maybe you can be better at capturing those indicators that are prior to the development of the cyclone. So maybe the direction is within weather forecasting and climate modeling. Then there maybe one can do interesting things.
Okay, Professor Gurnani, so I think you may kindly take over, and if there are no more questions, you may kindly conclude it.
Okay, sir.
Professor Gurnani, are you there?
Yes, sir, I'm there.
Okay.
So thanks to Professor Ricardo for sparing your time and delivering such a wonderful lecture. And it was a real honor it was a real honor for all of us to hear from you. And it was wonderful to see you touching like all the new areas in fluid with integration of AI and ML. And I'm sure like our students as well as professors and all external attendees today would surely be benefited out of it. So thanks a lot to Professor Ricardo once again, and on behalf of our group, and I hope to see you again in future addressing the IEM UEM family. And thanks to all the attendees for joining us. Wish you a great day ahead. Thank you.
Thank you very much. Have a good day.
Thank you. Thanks to all. Thanks to all attendees. Thanks to Professor. Thanks to Professor Ricardo. Thank you.